All right, we've got to talk about a really fundamental question in AI right now. Does a model actually need to be gigantic to be intelligent? You know, for years, the trend has been just to scale up, bigger and bigger. Well, a recent technical report basically says, hold on, maybe not. And frankly, it could be a massive game changer for the entire field. We're going to dig into this new frontier, building AI models that are smarter, not just bigger.
So, let's kick things off with a number, 227 million. That's how many core parameters we're talking about in the baseline language model for this study. Okay, now for the wild part. What if I told you that a huge chunk of all that complexity, all those connections was basically just dead weight? I mean, what if researchers found a way to surgically remove over 3/4 of those parameters and the model didn't just keep working? What if it actually got better? To really get why this is such a big deal, we first have to talk about the huge problem the AI industry is facing. It's kind of funny. It's a problem that was born from its own success, this relentless race for just sheer size.
Yeah, the whole strategy has been to just keep building bigger and bigger models. But this has created a condition that engineers call overparameterization. And in simple terms, it just means the models are bloated. They're packed with way more connections than they actually need, which makes them incredibly inefficient and just ridiculously expensive to train and to run. So, with these bloated models as the backdrop, where did the inspiration for a leaner, more efficient approach come from? Well, it didn't come from a faster supercomputer. It came from something much, much older and way more refined, our own biological brain. And when you put them side by side, the design philosophy is just night and day. You see, our artificial networks in their key layers often default to 100% connectivity. It's a dense, brute force approach. But the human brain? Oh, it's a masterpiece of efficiency. It uses what scientists call extreme sparsity, only firing up 1 in a quadrillion of its possible connections. Seriously, 1 in 10 to the 15th power. It really makes you wonder, have we just been over-engineering our AI this entire time?
This whole insight, inspired by the brain, led the researchers to a brilliant connection. And they found it by borrowing a technique from a field of AI you might not expect: computer vision.
So, inside these big language models, the main source of all that bloat, that overparameterization, comes from these things called dense layers. Sometimes you'll hear them called linear layers, and the name really says it all. They create this incredibly dense web where every single input is connected to every single output. This is where almost all of those 227 million parameters are living.
Now let's jump over to the world of AI that looks at images. In computer vision, there's a very similar-looking operation called a pointwise convolution. Its job is to mix information between the different channels of an image, like the red, green, and blue channels. And here's the critical part: it also uses a dense connection pattern. See where this is going? And this is the light bulb moment of the whole paper. It turns out that mathematically, a dense layer in a language model and a pointwise convolution in a vision model are the exact same operation. This was the key. It meant that a solution to make these things more efficient already existed. It was just hiding in plain sight in a different corner of AI research, ready to be applied to the most bloated parts of our language models.
Okay, so that's the theory, and it's a pretty compelling one. But does it actually work in practice? Well, let's dive into the experiment and see how they put these models in a head-to-head competition.
The researchers set up a really clean, controlled experiment. For their baseline, they used Microsoft's Phi-3 mini model. Then they built 2 new optimized versions using this efficient architecture, and they called them K-Phi-3. Now, to make it a totally fair fight, all 3 models were trained from scratch on the exact same data. And get this, to prove how accessible this method is, the entire experiment was run on just a single NVIDIA L4 GPU. So, the experiment is running. The models are training. What happened? Well, the results, they weren't at all what you might expect from a model that was put on such a strict parameter diet. In fact, these results directly challenge that whole bigger is better idea.
I mean, just look at this chart. The scale of the size reduction is absolutely staggering. On the left, you've got the baseline model, chugging along with its 227 million parameters. And the optimized Chi-Phi-3 models? One has just 35 million. That's an 85% reduction. And the other is only at 53 million. This isn't just trimming a little fat. This is a fundamentally different, leaner class of model.
Okay, so it's way, way smaller. Big deal, right? The real question, The one that actually matters is about performance. Can a model that's been so drastically pruned actually learn as well as its massive counterpart? And the data here is just fascinating. We're looking at a metric called validation loss. The easiest way to think about it is as an error score. The lower the number, the better the model is at learning and generalizing. So the huge baseline model scored a 1.58. The tiniest 35 million parameter model was right on its heels at 1.60. But here's the real shocker. The 53 million parameter model, which is just 23% of the original size, scored a 1.57. It was slightly better. Less was demonstrably more.
So let's zoom out. What does all of this actually mean for us? This isn't just some interesting academic exercise. No, this has really profound implications for the entire future of how we develop artificial intelligence.
For starters, this could signal a huge paradigm shift, moving us away from just brute force size and toward what you might call architectural elegance. It also seems to prove that making models smaller forces them to learn more efficiently. But maybe the most exciting implication here is the democratization of AI. Remember, this work was done on a single GPU in less than 3 days. That opens the door for a much, much wider community of researchers to actually contribute to the cutting edge of AI, not just the giant tech labs.
So, it really leaves us with this final thought. Is the future of AI about a race to build bigger and bigger digital brains, or is it about building smarter ones? Is it about brute force, or is it about taking a lesson from the elegant efficiency that nature has been refining for billions of years? This research seems to strongly suggest that the smarter path is the way to go.